Because it is unique to critical care transport, let's talk at least a little briefly about flight physiology. There are different physiologic zones that we have to be aware of. There are three that we're going to talk about here. Physiologic zones of the atmosphere. First is just a physiologic zone, anything below 10,000 feet, where we can maintain our own partial pressure of arterial oxygen. Most helicopters are going to function in this physiologic zone under 10,000 feet. Once we go over 10,000 feet, we enter into this physiologically deficient zone, and this is where we need some supplemental oxygen and/or need a pressurized aircraft, right? So think of flying in just a commercial aircraft. We're in this physiologic deficient zone, and we are in a pressurized aircraft. Above that, above 50,000 feet, is our space equivalent zone. So now in the space equivalent zone, supplemental oxygen and a pressurized aircraft is no longer adequate. So now we need a sealed cabin, and we need pressurized suits to maintain our partial pressure of oxygen. And with those changes in altitude, with those changes in barometric pressure, there are a number of gas laws that we have to be mindful of. First one that we'll talk about is Boyle's law, and that says that the volume of gas is going to expand as the pressure decreases. So as we go up in altitude, our pressure is decreasing, so the volume of gas is going to expand. This becomes very important because there's a risk of barotrauma as we go up in altitude. So there's free air in the body. That volume is going to expand. So think of an intubated patient, your ET tubes. We've got air in that balloon. That the volume of air is going to expand. Could burst that balloon. Or could cause trauma to the trachea. Same thing with nasogastric or OG tubes, air splints if you're transporting, flying a trauma patient, and the ground crew has put on air splints. We have to take this into account. The next gas law we have to be aware of is Charles's law, and that states that the volume of gas is going to expand as the temperature increases. So, volume of gas expands as the temperature goes up. With Charles's law, remember as we go up in altitude, the temperature is going to actually decrease. So it's going to have some effects on our compressed oxygen and other gases that we carry on board. Maybe you've got some nitrous oxide. Maybe you've got some heliox, and we have to monitor our patient and our crew. Just be mindful of our temperature and watching for hypothermia. And then we have Gay-Lussac's law, which states that the temperature of a gas increases as pressure increases. Or if we were to flip that around, the temperature of a gas decreases as pressure decreases. So if you've ever opened an oxygen tank all the way open, right, you feel the oxygen tank cool down and get cold. So again, something to be mindful of as we are administering gases like oxygen. As we open that up, the temperature is going to decrease as the pressure decreases. Next, we have Henry's law, which states that the amount of gas dissolved in the solution is directly proportional to the pressure of the gas over the solution, which sounds really complicated. But we encounter this probably daily, weekly. I don't know how often you drink soda, but open a can of soda, open a bottle of soda. There is gas dissolved in that solution, right? They've got carbon dioxide in there. When you open it, pressure is released. Pressure decreases, right? So the pressure of the gas decreases and it's released. And this gets into things like decompression sickness, right? The bends. Henry's law is directly applicable to that. So go to your fridge right now, open up a can of soda, and you are witnessing Henry's law. And we have Graham's law, which says how, or not says, but shows us how easily a gas moves across that membrane. And there are different gases, and they move across these membranes more easily than others. So carbon dioxide is more soluble than oxygen, right? So carbon dioxide will move, will diffuse more readily across that membrane than oxygen will. And finally, we have Dalton's law, which says that the pressure exerted by a mixture of gases is equal to the sum of all those pressures. So all of those partial pressures of each gas in that mixture. So this is just an additive law. So we see here we've got oxygen, nitrogen, argon, a little bit of water, some CO2, right? We've got just air. You're breathing in air. So the pressure of air is equal to the partial pressures of each of these gases. Becomes very important as we increase our altitude because we have to adjust our oxygen delivery as altitude increases. And there's a pretty quick and easy formula for adjusting FiO2 or the oxygen delivery to our patient. So we're going to take our initial FiO2, multiply that by our initial barometric pressure where we're starting, and then divide it by the barometric pressure at which we are flying. So let's say a non-pressurized aircraft, right? So our patient, just as an example, has an FiO2 of 70% or zero point 0.7, and we're going to multiply that by our initial barometric pressure. We are at sea level, so 760 millimeters of mercury is our initial barometric pressure. We're going up to an altitude in which the barometric pressure is 600 millimeters of mercury. What is the FiO2 needed to maintain that same oxygen delivery and partial pressure of oxygen? It's now going from 70% to just about 89%. So as we go up in altitude in a non-pressurized aircraft, we need to adjust our FiO2, and this quick and easy formula can help us do that. All right, we've talked gas laws and we've talked FiO2 adjustments and oxygen adjustments. So let's talk hypoxia. And there are 4 types of hypoxia that we're going to talk about today. And one of those is hypoxic hypoxia. There's a histotoxic hypoxia, there's stagnant hypoxia, and there's hypemic hypoxia. Now, the first of those is hypoxic hypoxia, and we can kind of think of this as like an altitude hypoxia. There's just a lack of oxygen entering and diffusing into the bloodstream. So it's a lack of oxygen and an inadequate availability of oxygen to our cells. So this lack of oxygen is going to reduce our PaO2. With histotoxic hypoxia, oxygen is available. It is there on our little hemoglobins and it's circulating around, but our tissues can't accept it. So there's reduced oxygen offloading. That's what histotoxic hypoxia is. We see this most commonly in alkalotic states, and if we go back to our Bohr effect, or think back to our Bohr effect, and think back to acid base, right? Bohr effect says that oxygen really, really likes hemoglobin in alkalotic states, in alkalotic environments. So, in our patients with in alkaloses, the oxygen is going to just stay there with the hemoglobin, and it's not going to offload. So, with histotoxic hypoxia, unlike hypoxic hypoxia, oxygen is available, it's just not offloading. Then we have stagnant hypoxia, And this is a failure to transport the oxygenated blood. So there's oxygen, it's there on our hemoglobins. We're just not transporting it, we're not circulating it. So there's slow blood flow, there's reduced blood flow, there's venous pooling. When we think of flight physiology, think of tight turns, think of g forces. So this is what happens. With increased g forces. So we've got a failure to transport this oxygenated blood to our cells. And finally, we have hypemic hypoxia or anemic hypoxia. So think of anemia. And then this type of hypoxia, we have a lack of red blood cells, a lack of hemoglobin. So we've got oxygen coming in, but there's just not enough hemoglobins to attach to. So, in traumatic states, or even non traumatic states like hemorrhage, and carbon monoxide poisoning as well, with our carbon monoxide taking up all of our hemoglobins, we just don't have the carrying capacity for the oxygen coming into the body. All right, the last thing we're going to mention here under flight physiology is just some flight precautions. Um, and there's some just very unique precautions, unique things we have to kind of be mindful of when flying. One is that spatial disorientation. So we're kind of out of our element, right? And maybe we're flying over some kind of nondescript I don't know, territory environments, and it would just get disoriented. It's got spatial disorientation. There's also flicker vertigo, in which it's vertigo, but it's brought about with like flashing lights and lights that are flickering, right? So what? Well, flicker vertigo, right? So we've got a rotor wing aircraft, and there are lights around that aircraft, and we've got those rotors going around, and that's going to cause or might cause some flicker vertigo as we see like lights flickering on and off and on and off and on and off. We've got G forces. We mentioned G forces a little bit earlier, but these gravitational forces, unique hazard here. In the aircraft, we've got barometric pressure that's going to differ as we go up in altitude, as we decrease in altitude, right? We've got differing barometric pressures, and with that, we've got decreases in humidity as we go up in altitude. Temperature is going to decrease, humidity is going to decrease. We're going to need different kind of fluid needs, right? The patient's going to need different fluid needs. So just these kind of unique hazards that are unique to the aircraft and not necessarily on your everyday ambulance. If you have any questions, comments, concerns, or cuss words, please let us know.